Hello, this is the next video in a playlist that I'm calling Applied Multivariate Analysis. And we're in chapter 2, which I'm calling the matrix algebra portion of that playlist. And let's just jump right in where we left off, which is page 18. And here we're going to look at the distance from the origin to a point A. Remember, A is a vector. And so you kind of think of vectors as this dangling arrow out in space somewhere. And if we want to find the length of that, this is how you do it. So the length of A will be denoted by these double vertical bars, which is really the square root of the dot product, or this is a vector product, which is equivalent to a dot product, which is the sum of the squared components. Now, since the sum of squared things, it has to be 0 or more. You can't have a negative length of a vector. As a matter of fact, if the length is 0, that implies that every component is 0, so it's the 0 vector. Now the dot product, a very brief geometric interpretation, which we will expand on in later videos, that we can show by the law of cosines that this dot product, A transpose B, is equal to the length of A times the length of B times the cosine of the angle between those two vectors, A and B. So remember that A and B are vectors, so they can be thought of as arrows starting at the origin and then going out in space and dangling out there somewhere. Well, there's an angle between those vectors, and that's what theta represents. So the dot product, A transpose B, is the length of A, and then this here, the length of B times the cosine of theta, is really the length of the projection of B onto A. And that's all we're going to do in this video. If you want a sneak preview, I'll point you to the first 7 minutes of this video, Projection Matrices Introduction, in a playlist that I think is denoted by matrix. Now, if we let our vector be little j, remember little j is a vector of all ones, and little j and capital J are so important in linear models and this multivariate analysis class. We're going to look at some of the properties. So j prime j, so this vector product, or you can think of it as a dot product, it just is n. It's the number of components, right? 1 times 1 plus 1 times 1 plus 1 times 1 all the way to n times. So we're summing 1 n times, so it's n. Now J transpose, this creates a n by n matrix of all ones, which we denoted by capital J. Now if we were to look at this in R, then J is we create a vector of ones, and then J transpose J is 10, right? It's the number of components, and then J times J transpose creates a 10 by 10 matrix of all ones. Now, if A is an n by 1 matrix, capital A is just a matrix n by P. If we look at A transpose J, remember J is a vector of all ones. When you do this product, it ends up just being the sum of whatever the elements of A are. And remember, and since this is a number and these are both vectors, you can actually take the transpose of it, which creates J transpose A. So it's the same thing. It's literally just the sum of the components of that vector. So if we have a vector J, we take a sample A, a vector A, random vector. J transpose A is 3. Transpose AJ is 3, right? It's just a number. And that's it. So now if we look at a matrix times J, so remember, so it's the first row times this vector J. So, and that just adds the first row, the elements of the first row. Then the second row times J adds the elements of row 2, and then so forth. So this vector, remember, this is n by p. This is a p by 1 vector, which creates an n by 1 vector, and the components are the row sums of A. Now if we do J out front, so J transpose A, so now J has to be an n by 1 vector, right? So the transpose is 1 by n. This is n by p. So this is a 1 by p vector. And it ends up that when you take this row vector of 1 times the first column, you create a column sum. And you do that for each column. So this is really the column sums of A. And you can see that in R. So if we have a vector J, we have a matrix, and then we want to add the columns, we take J transpose A, and this is it. This is the column sums, and we'll just look at one of them, -3. So -5 plus 2 is -3, and that's the same. These are the column sums. The row sums would be A times J, and this creates the row sums. And let's just look at one here. So we have -7 plus 0, that's 0. And that's what it is. So this is the row sums. Now, the matrix A, n by p, we can take it times itself, but we have to use the transpose. So if we go A transpose A, that creates a p by p matrix where each element of the resulting matrix is just the product of the columns of A. So it's the dot product of the columns. So A transpose is an n by n matrix, and all the elements are the dot products of the rows. And we'll look at that and note that both of these are symmetric. So if you take the transpose of this, you get it back. So it has to be symmetric. And so we have a matrix A, and we look at A transpose A, and we get so this is 4 by 2, so this creates a 2 by 2 matrix. But really, this entry of the result, so this is 1, 1. So it's the dot product of column 1 with itself, right? Boom, 108. So this one here is the dot product of column 1 and column 2. Should be 64, right? And since it's symmetric, we get 64 on both sides. And that last entry is the dot product of column 2 and column 2. And that's 100 right there. Now, if we take A times A transpose, then it's a 4 by 4 matrix, but it's the dot product of the rows of A. So this first entry, 58, since it's 1, 1, it's the dot product of row 1 with row 1, and it should be 58. Yep. This entry here is 1, 2, so it's row 1 dotted with row 2, and it should be 14. Row 1 dotted with itself, and it's dotted, right? This is a vector transpose times this vector, we get 14. And the same way for each of those. I don't go through all of them because there's just too many. Now the last concept is diagonal matrices, and when you're multiplying it times a matrix. So let A be an n by p matrix and D be an n by n diagonal matrix with entries D1, D2 to Dn. Now this is A, so these are the rows of A. Notice there's no parentheses around that 1. And there's n rows. So when you take this row times each column, it's zeros times everything here, but the D1 is always times that first row. And that's what it's saying right here. And you go down and it's the same. So it's really the ith row of A is multiplied by the ith element of D, the Di. And it's just the opposite here. So if we take A times D, then D, right? So when this is times this matrix, D1 is multiplied by the first column, and the rest are zeros. So these all drop out, and we're left with this entry. And it's the same all the way down. So when we multiply this column, times each row, because it's just the opposite. Sometimes people think, well, it's this row times this column, but it's also the same, this column times each row. These are all zeros, so the only thing that's being multiplied is that last column times dp. Yep. And so the jth column of this is really just multiplied by the jth diagonal, dj. And then to see this in R, and then we'll call her quits, we have a matrix A, and then a diagonal matrix, and I'm just going to call it 1, 2, 3, 4, right? So we can see this easily. So D times A is this. So note, so it'll be 1 times this first row, so 5 and 7, 5 and 7. Then it'll be 2 times the second row, which is minus 6 and 12, and be 3 times the third row, 4 times the fourth row. And then when I just printed A again so we could have it ready. But here, since we want to multiply A times D, D has to be conforming, so it's a 2 by 2 matrix. And then we're multiplying the the columns by each of these. So 1 times this first column is this result, right? We just get it back. And then 2 times the second column, which is this. And so the product works. Well, that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.